Hey guys, good evening, and we will. Okay, I have to see managing first. Okay, so we have done with chapter number 9, and today we will solve some of the problems from chapter 9. Okay. Although this chapter is about, as you know, this to do elasticity, and even if you have like a three-noded element, only one element, and then that becomes 6 by 6 distribution matrix, right? So it is the doing by hand is lengthy. If you see 6 by 6, there are 36 entries. Of course, it will be symmetric, so you can find out. But the thing is, it is suitable for doing the programming more than doing by hand. Yeah, so that's the main thing. But still, looking at the questions, let's just discuss the ways, like the procedure. Mostly, we will not solve the complete problem, but we just will look at and we find out how to solve them. Now 9.1, it says construct row 1 of B matrix for the 6 node triangle. Yeah. So 6 node triangle. And is a B matrix. So how to do it? Quickly, we discussed earlier also, you can construct, let us say 1, 2, 3, 4, 5, 6. You can construct Ni, X, Y as a function of, let's say alpha I plus beta I, X, gamma I, Y plus delta I, XY, right? Plus lambda I x square plus we put some other value. What else? New phi I y square. So you have 1, 2, 3, 4, 5, 6. Yeah, 6 coefficients, and you have 6 points, and you solve them, right? So Ni automatically, you know that N, for example, N1, if it is x1, y1 is equal to 1, right? Or Ni xi yi is equal to 1, right? Or you can also write x j and j equal to 1 if I equal to j, and Ni xj yj equal to 0 if I not equal to. So in general, you have that, and you find out the values of this coefficient, and you can solve it, and then construct the B matrix. As you know, that B matrix will have, once you have n B matrix, will have Remember? What does it have? Integration. No, for first. One x 0. It's fine. And n 1 y 0. And so on, right, till 6. So this will be 3 by 12. So once you have that, you construct it, you can do that. This is one way of doing it. You can also use this as isoparametric element. Right? So then use isoparametric element. The other way, you convert this to this one system, Xi1, Xi2 system. And you have exactly like this. And then you find out this is 1, this is 2, this is 3, right? These are 4, this is 5, this is 6, and then you have n, Xi1, Xi2, Ni. You find out what those values are. You have to, we have done already. Once you have that, and then here, only thing is, that these are linear basically. So when it comes to x you can write Xi1, Xi2 is equal to summation. This is 1 to 3 summation Ni. Yeah, Xi1, Xi2 as xi. So I equal to 1 to 1. We not write 6. There are not 6 of them, but since this is exactly in middle, if this is exactly in middle of this, then only 3. You have to write. Okay, you can write this in terms of only 3 shapes. Yeah. You follow what I am saying? If these nodes are exactly in the middle, yeah, in that case, when you attack, sorry. So exactly in middle, then what happens is this becomes redundant. There is no use of it. You will find that automatically you will get the value, the n, this value will be somehow, it will not be used. You can try yourself, right? It is used when you have a triangle like this. Right? So when you have like the edge itself is quadratic. In that case, you can write as I equal to 1 to 6. But otherwise not needed. Linearly, it scales automatically. Yeah. For example, if it is bit exactly here, then what happens? N1 becomes half. N3 becomes half multiplied by this. Automatically tells you that value. So it gives you that value, right? Automatically it gives you exact value. So why to include the other? Other will be just a repeat. There is no use. Okay, and accordingly, your other things like that you have to calculate j, and we have del x over del xi1, del y over del xi1, del x over del xi2, del y over del xi2. We know this, and also we know ln I over L xi 1 del ni over del xi 2 is equal to z del ni over del x del ni over del y. You know that, right? So we use this relation to find out the value of x. And this you put back to here to get the matrix. Yeah, so there are two ways of doing this. Next is show that for rigid body translation, epsilon xx strain vanishes. Let the nodal displacement be proportional to the coordinates. Find out the strain field. Does this answer make sense? For this problem only, if you have epsilon xx equal to prove 0 if rigid body motion. Rigid body motion means what? What is the meaning of that? Huh? Yeah, no movement into points. 0 is not correct. This is that really means they have some relationship between ux and uy. Right? It will not be 0. If it is has ux everywhere the same, right? Ux equal to 5. Okay. All points have the 5. It's possible, no? Displacement of all the points is equal to constant. This will be purely translation motion. Rotation will have, similarly, there is a relationship between them. Yeah. So here it says rigid body translation. It's a translation. Rigid body translation, that really means Wx equal to a constant. Ux equal to constant, u equal to another constant. So let's say ux equal to a, uy equal to b for all nodes. So the original triangle which is here changes, it goes here, such that this all is parallel. Right? So this is, let's call it equation. Let us say this is a vector v. So all are vector v1, where v is equal to ux I plus uyz. Right? So displacements, finite displacements are the same. You have to prove that the strain is 0. Then how will you do it? What is the strain? How do you calculate the strain? Strain is equal to, remember, we have B, and then we call it D matrix. You remember? Right? So their D matrix, D is equal to what? D will be, let us say in this case, you have 6 of them, right? So you have 1, 2, 3, then you have number 4 here, number 5, number 6, and so on. So you will have ux1, uy1, ux2, uy2, and so on till ux6, uy6. transpose of it. But this and this is the same. Everywhere it's same. So basically, what you have is it is everywhere the same value, and uh, value is, let us say, just to say this is a constant we are talking about, or maybe ux0. Let's put ux0 everywhere. So you have the same value everywhere. ux0, right? Yeah. So epsilon xx, if you have to calculate, epsilon xx will be nothing but whatever the first row is, means this one multiplied by that. Yeah. And automatically, since you know this one, you will multiply by this, you will get 0. You should get 0 is equal to the b first row multiplied by d. Yeah. And this will be equal to 0. Automatically, you will get it 0 for sure. Any question, guys, so far? Now it says that ux is proportional to x, means the coordinate itself. So that means ux1 is equal to alpha x1, uy1 is equal to alpha y1, and so on. ux2 is equal to alpha y2, x2, uy2 is alpha y2, and so on. And then you have to find out a strain field, and then you have to find out the strain. Right. So how will you do it? You compose D, which is equal to ux1, y1, ux2, uy2, and so on. Find out that, and so that strain is equal to P, right? And whatever the value you find out. So only thing is your D will be something like this, and then you find out what the value is. You have to calculate. Yeah. Okay. Any question? Okay, now let's go to second one, 9.2. It says a three-noded triangular element is subjected to a linear body force in the x direction given by Px equal to how? I did not get you second.
How the strain in this income, like multiplying by
If you work, you will get 0. Okay, this is I just predicted. Yeah, this is what we are supposed to do. Yeah, you also have to do some work. That's really means. Okay, so don't rely on me. Yeah, you have to prove I'm wrong. Okay. Yeah, that will be enough for me. Yeah, you will get 0. If you calculate the first, find out first row, you multiply by D, you will get 0, current. Yeah, it is just predicted. I did not calculate and write. I predicted it will be 0. Has to be 0 because this rigid body movement means all of them has moved the same. So there is no strain in that case. We just move from here to here. The strain is 0, it has to be 0. And numerically you will get 0. Yeah? Okay. 9.2, and it says that a granular element has a B, which is defined as B equal to B1 xi1 bx2, so bx1 xi1 bx2 xi2 bx3 xi3. Develop the expression for the nodal forces corresponding to this body force given in. Okay, so bx xi1 bx1 is I1 plus bx2 is I2 plus bx3 is I3. Nodal forces is equal to what? Nodal forces. And of course, in this case, you are assuming that here is I1, here is I2, 1, 0, 0, 1, 0, 0. Here you have 0.1, 0.2, 0.3. Yeah. Okay, and N1 is equal to N1 xi1 xi2 is equal to xi1 N2 xi1 xi2 is equal to xi2 N3 xi1 xi2 equal to xi3 is equal to 1 minus xi1 minus xi2. So we have that, and we have to calculate forces. And how to calculate forces? Remember that B is given by N B, where B is a vector. You are not B but force, which is given B. This equal to N B, and then you have, I think you have to T there, right? You write T there. So N is yeah. Okay, so B D omega. So this will be N. Here N is equal to, remember how do you write? N1 0, N2 0, and N3 0. Then you have 0 N1, 0 N2, 0 N3. This is how you write, right? This is N. But N transpose, then N is 2 by 6. N transpose becomes 6 by 2, and then this you have 2 by 1. 2 by 1. So that means what? The first one, for example, this is B, and hence B is given, which is equal to subjected to x direction given body force. So, okay, now V is equal to Vx at 0, where Vx is given as Vx1 psi1 plus px2 psi2 plus px3 psi3. Yeah, and then this is given as V. So this is what is given. Develop the expression for nodal forces. Okay, so when you transpose it, then what happens? You have this multiplied by this one. So n transpose, if you say, then you get value as n1 0, n2 0, n3 0, then 0 n1 0, n2 0, n3, and then you are multiplying. So this B is equal to, like this, dx1 psi1 plus, right? So bx2 psi2, bx3 psi3. Guys, this is supposed to be tutorial, and coming here solving problem probably may not work. Basically, this is not replacement of your doing the work. Yeah, tutorial is supposed to you solve, and I come and check whether you have solved right or not. If you have problem, you ask me. Yeah, but I just do for the benefit of it. So if it is not working, let me know. So in that case, I will not do. And then you will do, and then I will come. Only what happens if you can solve 1-2 problems only in that case. Here, I think discussing a problem basically makes it more clear for me. So before coming to the class, you are supposed to solve already, then come to the class. Yeah, not that master comes and you are waiting. Let him do all the work. Yeah, so only you will not gain anything out of it. Yeah. Okay. So we have, what you get? This multiplied by this multiplied by this multiplied by this, and so on, right? So what we will get? We will get the force will have automatically FB, it will have some value. Let's call it FB x1, then it will be 0, FB x2 0, FB x3 0. Why 0? Because you can see, if you see number 2, this multiplied by this, 0 multiplied by this, 0 multiplied by this, so becomes 0. So every other one you get 0 only. This one you have to find out. Where FBX1, for example, will be equal to N1, right? XY, whatever we have XY. And then what do you get? N1 XY, and then you have what else? B, right? This value. So which is equal to bx1 xy1 plus bx2 xy2 plus bx3 xy3. Okay, omega, and here you have d omega. Yeah. Fine. So this is what is supposed to be. Now you have to convert that into xi eta system, that we have to do. And how do you do? We have to convert this into xi atom. Yeah. So in I, automatically this depends on not xi atom, xi1, xi2 system, and this we know that for one we have one only, and you have xi1, so you have xi1, and n1 equal to xi1, so you write that. Then you have dx1 xi1 plus dx2 xi2 plus dx3 xi3, and then you have this, and this is what triangular system you have to convert into. So you have j here, and then you have b xi2 b xi1, and you have 0 to what? 1 minus xi1, 0 to 1. Right? And you work on it, you can find out what the value is. You are multiplying by this and right. Yeah. Any question? Number 3, consider a quadrilateral domain model of unique thickness with a single finite element as shown in the figure. All dimensions are in figures. Meters. The traction applied on the edge 1, 2, okay, is normal to the edge and is given by 6 dot n. Okay, where n is a unit vector normal to edge. Calculate the element boundary force matrix. Okay, so 9.3 we will do, which is easy. Okay, guys, in lot of Western countries, you don't have tutorial. Okay, in US, there will not be any tutorial. Yes, you are going to miss it. Okay, so you will miss it here. Yeah, they have what is called the office hour, during which professor will be available. You can ask questions. Here, professor comes and tells you, you ask questions, but still you don't ask. Just think about it. 200. 3 1.20 4 1.2 5 0.6. Okay, so this question is now talking about how to construct the force vector into the bound. Yeah, so we are looking at a different aspect. The first, we have to compute the B matrix, but for the 6-noded one. Number 2, given the force vector, you have to find out what is the means the body force, what is the nodal forces. Number 3, you have a traction like this. Yeah, so where the some value is given, which is equal to 6 dot n, 6 dot n Newton per meter only. So we say per meter square is fine, but thickness is say equal to 1. Right? So thickness, whenever it is says per meter square, you have to know the thickness as well. Yeah? So then you have to look for the thickness is given. It says the unit thickness. Right? Thickness equal to 1. So effectively it is Newton per meter if you multiply by 1. So this is perpendicular to the surface length. Okay, so this is okay. Now given that, and you have to find out, right? So force vector as such will be what? If because of what? Because of the surface, so let's call it Fs. And then this is a vector which will be F, right? And then we can have this one as x1, f x2, f sorry y1, if there are 4 of them, right? So 1, 2, 3, 4. So x2, fy2, fx3, fy3, fx4, fy4. Now, just looking at it, can you tell what will be the value of, say, fx3? It will be 0. This will be 0. This will be 0. This will be 0. Because there is no surface forces here. There is no forces on this one, so this becomes 0 here. There is no force here, so 0 goes, half 0 goes here, so half goes here, here. And you know that each node here you have forces. For example, here it will be F, what is 3, Fx3, this is F, Y3, Fx4, Fy4, and so on. Right? So from there we are relating. Only we have to calculate this one, and from there we get all these values. So how do you do? What I would do, you just apply some common sense we learned. Yeah, it is something that insight you have now because you have attended my class. Yeah, at least. Okay, so if you have this 6.n, so 6 multiplied by what is the length of that? L. So you have L, which is equal to, you can find out from here to here. So here to here this is 0.6, from here to 1.5. So multiplied by 0.6 square plus 1.5 square. Yeah, is it? Is it correct?
Yes.
So whatever the value you get, multiplied, this is multiplied, and then divided by 2 will be what this value. Right? So from here to here, let's call it F1, right? F2, sorry, this will be F2, and this is F1, right? So this is equal to F1 is equal to F2. Both will be this value, right? Only thing is now that how to divide it into components. That's what you need to do. So how do you divide? So this is what it is. This is like this and like this. This equal to this plus this, right? So the value which goes upward is what? Fy1. Oh, sorry, this is 2. Fy2. And what is the value? What is this one? From here to here? This is minus minus of what we know it as f y x2. And hence we can now find out what will be the value of those. Yeah. So component of this, so what is the angle? So let us say the angle here is theta, right? So this angle, so this will also be theta, right? And that really means this will be same theta, right? You agree? Yeah. Is it correct or not? Okay. So theta here, so this and this theta, so from here to here 90 degree, so 90 minus theta, so theta has to be there. So that really means we can find out the relationship now. And what do you get? You get cos theta. Cos theta is equal to f minus f x2 divided by f2. This value. And sin theta is equal to f y2 divided by f2. Yeah. And where you can find out sin theta is equal to sin theta, you can find out from here. So sin theta is 0. This is 0.6. So 0.6 divided by root 0.6 square plus 1.5 square. And cos theta accordingly is 1.5 divided by root 0.6 square plus 1.5 square. Yeah. And you can calculate, right? Similarly, we know that this and this will be equal, and this and this will be equal. So this is how you will do as insight. If you want to use N1, N2, that also you can do. Yeah, and you know how to proceed for that. How will you proceed? You will proceed as this is the bounded forces. What do you call it? Traction. So this is the value, right? So this is the traction T, which is given, is equal to Tx and Ty. That's given, and then the force. What is given? You are going on. Finally, the thing that we work on. Remember, we are working on N, right? Transpose of that. These are the similar expression as the body force, right? So N transpose, and then you have what? T. Exactly the same. Basically, instead of B, you have T here, and we will have become.
T dot
Huh?
T dot
T dot N. No. That's already taken care of, no? Yeah. Final value, this T itself will have Tx and Ty, and Tx Ty already that has already T dot N comes here. A component goes here. This is the final. Right? Thus T is the surface force, final surface force, perpendicular to that. And here also you have the perpendicular only. Okay, so Fine. Okay. And then you know already, of course, this will be equal to only where this is applied. What is applied? Gamma t only. And then n t gamma and t bar t tilde is equal to nothing but you have tx and ty, right? And here tx and ty, you can find out the component of it. And how do you find out? This one is the same thing we have done as earlier. So if the value here, this is the final value. So what you get is this will be ty, right? And this will be minus tx. Yeah? So this value, where this is theta, this value goes here, this value goes here. These will be numerical values. Yeah? And then that you multiply there and do it. Okay. Yeah. Finally, we are looking at what? We are looking at the this force, the component of that, and then we are just use as the body force. Of course, you have n, and then only the n1 and n2 will vary here. N3 will be 0 here, so you get 0 corresponding to 0.3. Then you have node 4, you will get 0 corresponding to. So all these two forces will be 0, these two forces will be 0. For this one, you will see that for both the components you get half and half. So finally, the whatever way you calculated here, you do the same way. Yeah. Don't be confused regarding what to put here. Remember that this is the final force we are talking about. Yeah. This one is already taken care of. Final, like K U equal to F. Final value has to be a stiffness, displacement equal to force. You have to get in terms of force only. This is the distributed load. Final, whatever you are writing here, this is nothing but we are talking about the distributed load only at the boundary. Yeah, distributed load not necessarily will have perpendicular to the surface. It's not like that. Yeah, it can be surface, like it can be in some problem. It can be some shear load which is going to apply here, and accordingly for you T will be this, and you see take both the components of that. That's it. It can be in any direction, right? Any question? You just look at the force and you just. Similarly, for heat transfer here, whatever you get is what is the heat loss, right? And heat loss, whatever you written there is in terms of Q dot N, because here the idea is you are giving the net, what is the heat loss from the surface. Yeah. Here there are two components of that. Forces in this direction and that direction. So both direction, what you have is what is the force in x direction, what is the force in y direction, and hence you get in vector form. In heat law, heat transfer problem, this is a scalar only, so you don't have x and y component. It is just heat loss. That's it. Okay, I think we take one more question. Okay. because I came late. It's fine with you guys? Okay. Fluid mechanics or mechanics in general, whether it's fluid mechanics, it has a lot of insight basically. You don't have to memorize the equations. A lot of times equations are just to formalize it. Yeah. So now 9.16. This is a triangle, something like this, and then you have forces. Okay, and then one force here, one force here, one force here, one force. Yeah. Everything is given in this case. What is given? You have the elastic properties. E is given, nu is given. E is equal to 3 times 10 to power 11 Pascal. Nu is equal to 0.3. The essential boundary conditions are UAX, UAY, UBY is equal to 0. So this is fixed, and here we have a roller. The initial boundary conditions as follows. Along each edge of the panel, the prescribed traction consists of normal and neutral components, both equal to 10 to power 3 Newton per meter. 10 to power 3 Newton per meter, both of them. Both of means these also and these also. Discretize the panel using a single rectangular element as shown in the below. For convenience, use identical global and local coordinate system. Calculate the nodal displacement as stresses at element Gauss points. Yeah. And you have node numbering, which is you have to use at 1, 2, 3, 4. 1, 2, 3, 4. Okay. And you just have to find out what is the nodal displacement and stresses. What you have to find out, mu x I equal to what, and nodal, and then stresses, nodal displacement and stresses at the element Gauss points. So what is this one? Then there will be a Gauss points. Yeah, so Gauss points will be, that is, yeah. So you know that, right? These are the Gauss points, let us say. And it is asking you sigma at this. So how will you proceed? 1 meter and 2 meter. So here to here is the 2 meter. Here is 1 meter. Okay. Is it difficult, easy? What do you think? Will you able to solve it?
But building a single element, but then assembling all of them,
Single element.
then we have to assemble also.
Assemble it. Single element, do you need to assemble?
Like we have to distribute this into 4 elements.
No, who said? These are Gauss points. These are 4 Gauss points. You can also have a single point. Did not mention basically, so you just have Gauss points. Huh?
If you discretize the panel, then what has that?
You forget this one. This is just for, you have a single element like this one, you have to calculate. Okay. And how will you do it? I'm not getting your question. Say again.
So it is saying like discretize the panel using a single rectangular element.
Oh, so means only one element. Yeah. That really means you don't discretize it basically. Just use the whatever is given, you use the element. Yeah, that really means.
So if we do it by discretization into 4 elements,
That's not the question here. Yeah, but you can ask question. Yes. Then what happens?
then so then I'm saying like then assembling all of them will be difficult. Then that will need programming. Right.
Can you solve this one where for only one element? Can you solve it?
Right. No, we can try.
So first solve this one, man. Okay, and then you talk about 4 elements. You know, if you understand this one, you will understand that also. You know, so I'm talking about whether you will be able to solve this. Yeah, and main thing here is finding out the if you say u vector, right? This is a u vector which will have how many the displacements, right? So whatever displacement you will write here. This is number 1, 2. First will be, second will be, third will be. We don't know. So we write ux2. Number 4. Then ux3, uy3, ux4, uy4. You start with this. You got the u now. Now f. Okay. Can you find out what the forces? Little bit complicated, but you can find out. So this is all upwards, and it says that 1000 Newton per meter multiplied by 2 meter. How much you get here? 2000 divided by 2, which is equal to 1000. So you get 1000 here in because of this. So you get 1000. Sorry, in y direction. So let's say 0, 1000 here. Okay, and same thing you get. So let me write it here rather than there, because we also have to add. So 0, 1000. Now let's. This is 1. This is 2. This is 3. This is 4. This is 5. This is 6, 7, 8. This is a whole number basically we are talking about, right? So we have here, because of this one, we will have number 2 and number 4, right? So we have like this one. So this we are done with. Now this guy, same way, but it goes to x component. right? So you have 1000 here, will be 0 plus 1000 plus 0. So we are done this one.
It could be 500.
Huh?
Length is 1.
No, I did not get it. Second.
Length is 1.
No, I'm talking about this one, you know. I'm talking about this now. This is also distributed load only. A shear. Okay? This is also a distributed load, something like this only, but this is a shear. Right? Okay, what about this? If you have this one, then what happens? So you have 6 and 8, but minus direction. Yeah. So 1, 2, 3, 4, 5, 6. Right? You get from here. Similarly, you have here also, which will be minus direction. So you have minus 1000, minus 1000, right? Plus 0, plus 0 you do. So we are done this one and this one as well. Now left side, 1 and 7, and you will have half of it, 500, right? So 1 and 7. So 1 have, so 500 and 7 right here, 500. So we get it. This one will be 3 and 5. This one, right? 3 and 5 minus 500. So 1, 2, 3 minus 500 and 5. 3, 4, 5. This is also minus 500. Right? So this is also done. Now 2 and 8 plus 500. So plus 500 and plus 500. So this is also done. And here it will be minus 500. Which one? 4 and 6. So 1, 2, 3, 4. Minus 500 and 6, 7, 8. Minus 500. So whatever you get here, you write here. 1500, 1500, 500, 500, minus 1500, minus 1500, minus 500, and minus 500 again. So we get the forces. So we get that. Now this is just a simple rectangular element. You can find out what is the distribution matrix. You solve it. You get it. Right? Any question? Yeah. So you have to add. Yeah. So reaction forces here, you write in this case plus. Reaction forces also you have to include. So you can write it here. So you write plus R x1 plus R y1 then plus R y2. This will give you reaction automatically. Yeah, you solve it, you find out what is the value. Yeah. So you can find out. And once you have that, you apply all those formula to find out sigma. Sigma, how you find out? Sigma is, you have to find out first the strain, and T multiplied by a strain will give you a stress. Inside any software, these are it goes in background. Yeah. So you can now think about. Now you can. Main thing is like understanding that it's not that you go and click and you get some nice photo that means your analysis is good. It's not like that, right? You see what is the simplification you have done, what is the whether you get the values which are correct or not. So those things are important. Okay. You can use a single point. In this case, since there is no body force, so and your shape functions are bilinear, meaning that you have x, y term. Yeah. So for that, a single point will work. Yeah. So you can use that. Any question? Any question? Those who are online. Okay. If there is no question, guys, enjoy the holidays and see you Monday.